Learning objectives. In this chapter, the user would learn the following in detail. General register organization. Memory stack. One address and two address instructions. Data transfer. Arithmetic, logical and shift instructions. Software and hardware interrupts. Arithmetic and instruction pipelines. Central processing unit. The core part of the computer that performs bulk of data processing operations is called the central processing unit, CPU. Three major components are register set, arithmetic logic unit, and control unit. Register set stores intermediate data used during the execution of the instructions. ALU performs required micro-operations for executing the instructions. The control unit monitors the transfer of information among the registers and the operations at ALU. CPU organizations. The three most common CPU organizations: single accumulator organization, general register organization, stack organization, single accumulator organization. All operations are performed with an implied accumulator register. The instruction format in this type uses one address field. General register organization. This format needs 3 or 2 register address fields. Each address field may specify register or a memory word. Stack organization. Push and pop instructions which require an address field. Operation type instructions do not need an address field because the operation is performed only on items at the top of the stack. To store pointers, counters, return addresses, temporary results, and partial products during multiplication are stored in CPU registers. Referring memory for such applications are time-consuming process. It is more convenient to store the intermediate results in processor registers. All the registers are connected by a common bus. Bus system. Output of each register is connected to two multiplexers, MUX, to form the two buses A and B. The selection lines in each multiplexer select one register or the input data for the particular bus. The A and B buses form the inputs to a common arithmetic logic unit, ALU. The operation selected in the ALU determines the arithmetic or logic micro-operation that is to be performed. The result of ALU is available for output and also goes into the inputs of all the registers. The register that receives the information from the output bus is selected by a decoder. The decoder activates one of the register load inputs, thus providing a transfer path between the data in the output bus and the inputs of the selected destination register. Control unit provides the control signal for the operation. Control word. The combined value of the 14 binary selection inputs is called a control word. The size of the control word is 14 bits. It consists of 4 fields. 3 fields contain 3 bits each. One field has 5 bits. The 3 bits of SELA selects the source register for A input. 3 bits SELB selects another source register for B input. 3 bits SELD selects the destination register using a decoder, and 5 bits of OPR selects one of the operations in the ALU. Encoding of register selection fields are shown. When SELA or SELB is 000, the corresponding multiplexer selects the external input data. When SELD is equal to 000, no destination register is selected but to the external output. ALU, Arithmetic Logic Unit. The ALU provides arithmetic and logic operations. In addition, the CPU must provide shift operations. Encoding of ALU operations. Examples of micro operations for the CPU. Memory stack. LIFO, last in, first out. A stack is a storage device that stores information in such a manner that the item stored last is the first item retrieved. The CPU of most computers is a stack or last in, first out, LIFO. Very useful feature for nested subroutines and nested loops control. Also efficient for arithmetic expression evaluation. Stack pointer. Stack pointer always points to the top of the stack. Only push and pop operations are available for insert and retrieve data items. These operations are simulated by incrementing or decrementing the SP register. Stack can be organized in two ways called register stack and memory stack. Register stack, a collection of finite number of memory words or registers, are arranged as a stack. The stack pointer register SP contains a binary number whose value is equal to the address of the word which is currently on top of the stack. Register stack. There are three elements placed in the stack A, B and C in that order. Item C is on the top of the stack so that the content of SP is now 3. In a 64-word stack, the stack pointer contains 6 bits because 26 is equal to 64. Since SP has only 6 bits, it cannot exceed a number greater than 63, 1, 1, 1, 1, 1, 1. When 63 is incremented by 1, the result is 0 since 1, 1, 1, 1, 1, 1 plus 1 is equal to 1, 0, 0, 0, 0, 0, 0. But SP can accommodate only the 6 LSB. Similarly, when 0, 0, 0, 0, 0, 0 is decremented by 1, the result is 1, 1, 1, 1, 1, 1. The 1-bit register full is set to 1 when the stack is full, and the 1-bit register empty is set to 1 when the stack is empty. DR is the data register that holds the binary data to be written into or read out of the stack. Push operation. Initially, SP is cleared to 0, empty is set to 1, and full is cleared to 0. So SP points the address 0. If the stack is not full, a new item is inserted. First item is stored at address 1. The last item is stored at 0. If SP reaches 0, the stack is full. So full is set with 1. Pop operation. An item is deleted from the stack if the stack is not empty. Empty equals 0. The stack pointer is decremented at every pop operation. If it reaches 0, the stack is empty. Memory stack. A stack can exist as a standalone unit as above or can be implemented in a random access instruction fetch memory attached to a CPU. The program counter's PC points to the address of the next instruction in the program. The address register's AR points to an array of data. The SP points to the top of the stack. The three registers are connected to a common address bus, and either one can provide an address for memory. PC is used during the fetch phase to read an instruction. AR is used during the execute phase to read an operand. SP is used to push or pop items into or from the stack. Stack limits. Stack limits are checked with upper limit 3000 register and lower limit 4001 register. After a push operation, SP is compared with the upper limit register, and after a pop operation, SP is compared with the lower limit register. The advantage of a memory stack is that the CPU can refer to it without having to specify an address, since the address is always available and automatically updated in the stack pointer. The two micro operations needed for either the push or pop are 1. An access to the memory through SP and 2. Updating SP. Reverse polish notation (RPN). A stack organization is very effective for evaluating arithmetic expressions. The common arithmetic expressions are written in infix notation with each operator written between the operands. Consider the simple arithmetic expression A star B plus C star D. The reverse polish notation as AB star CB star plus. For example, arithmetic expression A plus B infix notation, plus AB prefix or polish notation, AB plus postfix or reverse polish notation. The reverse polish notation is very suitable for stack manipulation. Conversion to RPN. Consider the expression A plus B star C star D plus E plus F. AB plus DE plus C star F plus star. Evaluation of arithmetic expressions. Any arithmetic expression can be expressed in parenthesis-free polish notation, including reverse polish notation. Instruction format. Computer can have many instruction formats. It is the function of the control unit to interpret each instruction and provide the necessary control functions. The bits of the instruction are divided into groups called fields. The most common fields are: Operation code field specifies the operation to be performed. Address field designates memory address or a processor register. Mode field specifies the way the operand or the effective address is determined. Register address. Operations specified by computer instructions are executed on some data stored in memory or processor registers. Operands residing in memory are specified by their memory address. Operands residing in processor registers are specified with a register address. A register address is a binary number of k bits that defines one of 2000 registers in the CPU. Thus, a CPU with 16 processor registers R0 through R15 will have a register address field of 4 bits. The binary number 0101, for example, will designate register R5. The number of address fields in the instruction format of a computer depends on the internal organization of its registers. Instruction address fields. Program to evaluate X equals A plus B star C plus D. 3 address instructions. The advantage of the 3 address format is that it results in short programs. The disadvantage is that the binary coded instructions require too many bits. 2 address instructions. Computers with 2 address instructions are the most common in commercial computers. 1 address instructions uses an implied AC register for all data manipulation. For multiplication and division, there is a need for a second register. However, we will neglect the second register. T is the address of a temporary memory location required for storing the intermediate result. 0 address instructions. It can be found in a stack-organized computer. To evaluate an arithmetic expression, it is necessary to convert the expression into reverse Polish notation. The name 0 address is given because of the absence of an address field in the instruction. RISC instructions. The instruction set of a typical RISC reduced instruction set computer processor is restricted to the use of load and store instructions when communicating between memory and CPU. The following is a program to evaluate X equals A plus B multiplied by C plus D. Addressing modes specifies a rule for interpreting or modifying the address field of the instruction before the operand is actually referenced. Variety of addressing modes. To give programming flexibility to the user by providing facilities like pointers to memory, counters for loop, indexing of data, and program relocation. to reduce the number of bits in the addressing field of the instruction. The control unit of a computer is designed to go through an instruction cycle that is divided into three major phases: fetch the instruction from memory, decode the instruction, execute the instruction. Program counter (PC). It keeps track of the instructions in the program stored in the memory. PC holds the address of the instruction to be executed next and is incremented each time an instruction is fetched from memory. Mode field. An example of an instruction format with a distinct addressing mode field is shown here. The operation code specifies the operation to be performed. The mode field is used to locate the operands needed for the operation. There may or may not be an address field in the instruction. If there is an address field, it may designate a memory address or a processor register. Various addressing modes. Implied mode. Addresses of the operands are specified implicitly in the definition of the instruction. No need to specify address in the instruction. Zero address instruction in a stack organized computer is implied mode, since the operands are implied to be on top of the stack. Immediate mode. Instead of specifying the address of the operand, operand itself is specified. No need to specify address in the instruction. It has an operand field rather than an address field. Sometimes requires more bits than the address. Fast to acquire an operand. When the address field specifies a processor register, the instruction is said to be in the register mode. Register mode. Address specified in the instruction is the register address. Designated operand needs to be in a register. Shorter address than the memory address. Saving address field in the instruction. Faster to acquire an operand than the memory addressing. A k-bit field can specify any one of the two k registers. Register indirect mode. Instruction specifies a register which contains the memory address of the operand. Saving instruction bits since register address is shorter than the memory address. Slower to acquire an operand than both the register addressing and the memory addressing. Register used in register indirect mode may have auto-increment or auto-decrement features. When the address in the register is used to access memory, the value in the register is incremented or decremented by 1 automatically. Direct address mode. The effective address is equal to the address part of the instruction. The operand resides in memory and its address is given directly by the address field of the instruction. In a branch type instruction, the address field specifies the actual branch address. Faster than the other memory addressing modes. Too many bits are needed to specify the address for a large physical memory space. Indirect address mode. The address field of an instruction gives the address where the effective address is stored in memory. Control fetches the instruction from memory and uses its address part to access memory again to read the effective address. Slow to acquire an operand because of an additional memory access. Effective address equals address part of instruction plus content of CPU register. Relative address modes. The content of the PC is added to the address part of the instruction in order to obtain the effective address. Address field of the instruction is usually a signed number, 2's, which can be either positive or negative. Large physical memory can be accessed with a small number of address bits. PC relative addressing mode. R equals PC. EA equals PC plus IR address. Indexed addressing mode. The content of an index register is added to the address part of the instruction to obtain effective address. The index register is a special CPU register that contains an index value. The distance between the beginning address and the address of the operand is the index value stored in the index register. Indexed addressing mode R equals IX, where IX is index register. EA equals IX plus IR address. Base register addressing mode. The content of a base register is added to the address part of the instruction to obtain the effective address. A base register holds the base address, and the address field gives a displacement relative to this base address. Base register addressing mode. R equals BAR, where BAR equals base address register. EA equals BAR plus IR address. Numerical example for addressing modes. Various addressing modes. Data transfer and manipulation. Set of basic operations. Most computer instructions can be classified into three categories. Data transfer instructions, transfer of data. Data manipulation instructions, perform operations on data. Program control instructions, provide decision making and change the path taken by the program when executed in the computer. Data transfer instructions. Data transfer instructions cause transfer of data from one location to another location without changing the binary information content. Transfers are between memory and processor registers. Processor register and input or output. Between the processor registers themselves. The load instruction used to designate a transfer from memory to processor register, usually an accumulator. The store to transfer from a processor register into memory. Move used with multiple CPU registers to designate a transfer from one register to another, also from registers and memory or between memory words. Data transfer instructions. The exchange instruction swaps the information between two registers or a register and a memory word. The input and output instructions transfer data among processor registers and input-output devices. The push and pop instructions transfer data between processor register and a memory stack. Data manipulation instructions. Data manipulation instructions perform operations on data and provide the computational capabilities for the computer. It is divided into three basic types: arithmetic instructions, logical and bit manipulation instructions, shift instructions. Arithmetic instructions. The four basic operations are addition, subtraction, multiplication, and division. Add, subtract, multiply, and divide instructions may be available for different types of data. An arithmetic instruction may specify fixed point or floating point data, binary or decimal data, single precision or double precision data. Arithmetic instructions. Arithmetic instructions. A special carry flip-flop is used to store the carry from an operation. The add with carry performs the addition on two operands and the value of the carry from the previous computation. Similarly, the subtract with borrow. The negate instruction forms the 2's complement of a number. The mnemonics for three add instructions that specify different data types are shown. Add I. Add two binary integer numbers. Add F. Add two floating point numbers. Add D. Add two decimal numbers in BCD. Logical and bit manipulation instructions. Logical instructions perform binary operations on strings of bits stored in registers. They are useful for manipulation of individual bits or a group of bits that represent binary coded information. The logical instructions consider each bit of the operand separately and treat it as a Boolean variable. The clear instruction causes the specified operand to be replaced by zeros. The complement produces the ones component by inverting all the bits of the operand. The AND, OR, and XOR produces corresponding logical operations on individual bits of the operands. There are 3-bit manipulation operations possible. A selected bit can be cleared to 0 or can be set to 1 or can be complemented. Clear selected bits. The AND operation is used to clear a bit or a selected group of bits of an operand. For any Boolean variable x, the relationships xb0 is equal to 0 and xb1 is equal to x. The AND instruction is also called a mask because it masks or inserts zeros in a selected portion of an operand. Set selected bits. The OR instruction is used to set a bit or a selected group of bits of an operand. For any Boolean variable x, the relationships x plus 0 equals x and x plus 1 equals 1. Complement selected bits. The XOR instruction is used to selectively complement bits of an operand. This is because of the Boolean relationships x1 equals x dash, x0 equals x. Shift instructions. Shifts are operations in which the bits of a word are moved to the left or right. The logical shift inserts 0 at the leftmost position for shift right, at the rightmost position for shift left. Shift instructions. Arithmetic shift right instruction preserves the sign bit in the leftmost position and the bits are shifted towards right, including the sign bit. Arithmetic shift left is same as logical shift left. The rotate left through carry instruction transfers the carry bit into the rightmost bit position of the register, transfers the leftmost bit into the carry, and at the same time shifts the entire register to the left. Some computers have a multiple field format for the shift microinstructions. One field contains the operations code and others specify the type of shift and the number of times that an operand is to be shifted. Here, OP is the operation code field, reg is a register address that specifies the location of the operand. Type is a 2-bit field specifying the 4 different types of shifts. RL is a 1-bit field specifying a shift right or left. And count is a k-bit field specifying up to 2k-1 shifts. Interrupt. An interrupt is a special signal that causes the computer's central processing unit to suspend what it is doing and transfers its control to a special program called an interrupt handler. The responsibility of an interrupt handler is to determine what caused the interrupt, service the interrupt, and then return the control to the point from where the interrupt was caused. Software and hardware interrupts. An interrupt is a signal to the processor emitted by hardware or software indicating an event that needs immediate attention. An interrupt alerts the processor to a high priority condition requiring the interruption of the current code the processor is executing, the current thread. The processor responds by suspending its current activities, saving its state, and executing a small program called an interrupt handler or interrupt service routine (ISR) to deal with the event. This interruption is temporary, and after the interrupt handler finishes, the processor resumes execution of the previous thread. There are 2 types of interrupts: hardware interrupt and software interrupt. Hardware interrupt. This interrupt is caused by some external device such as request to start an input-output or occurrence of a hardware failure. A hardware interrupt is an electronic alerting signal sent to the processor from an external device, either a part of the computer itself, such as a disk controller, or an external peripheral. For example, pressing a key on the keyboard or moving the mouse triggers hardware interrupts that cause the processor to read the keystroke or mouse position. Unlike the software type below, hardware interrupts are asynchronous and can occur in the middle of an instruction execution, requires additional care in programming. The act of initiating a hardware interrupt is referred to as an interrupt request, IRQ. Software interrupt. Software interrupts are initiated by executing an instruction. This interrupt can be invoked with the help of INT instruction. A programmer triggered this event that immediately stops execution of the program and passes execution over to the INT handler. The INT handler is usually a part of the operating system and determines the action to be taken, for example, output to the screen, execute file, etc. Thus, a software interrupt, as its name suggests, is driven by a software instruction, and a hardware interrupt is the result of external causes. Software interrupt. A software interrupt is caused either by an exceptional condition in the processor itself or a special instruction in the instruction set which causes an interrupt when it is executed. The former is often called a trap or exception and is used for errors or events occurring during program execution that is exceptional enough that they cannot be handled within the program itself. For example, if the processor's arithmetic logic unit is commanded to divide a number by 0, this impossible demand will cause a divide by 0 exception, perhaps causing the computer to abandon the calculation or display an error message. Software interrupt instructions function similar to subroutine calls and are used for a variety of purposes, such as to request services from low-level system software such as device drivers. For example, computers often use software interrupt instructions to communicate with the disk controller to request data to be read or written to the disk. Arithmetic and instruction pipelining. It is a technique of decomposing a sequential process into sub-operations, each sub-process being executed in a special dedicated segment that operates concurrently with all other segments. The name pipeline implies a flow of information analogous to an industrial assembly line. Binary data flows from one segment to the next one during a clock pulse. Each segment is a combinational circuit with its results stored in a register at each clock pulse. Pipelining. For example, to perform the combine, multiply and add operations with a stream of numbers AI star BI plus CI for I 1, 2, 3, 4, 5, 6, 7. Each sub-operation is to be implemented in a segment within a pipeline. The sub-operations performed in each segment of the pipeline are as follows. Pipelining. All 5 registers are loaded with new data with every clock pulse. The first clock pulse transfers A1 and B1 into R1 and R2. The second clock pulse transfers A2 and B2 into R1 and R2. The third clock pulse operates on all 3 segments simultaneously. It places A3 and B3 into R1 and R2, transfers the product of R1 star R2 into R5. General considerations. The general structure of a 4-segment pipeline is illustrated. K-segment pipeline with clock cycle time Tp is used to execute n tasks. The first task requires a time equal to KTP to complete its operation since K segments in the pipe. To complete n tasks using a K-segment pipeline requires K plus n-1 clock cycles. For example, 6 tasks with 4 segment takes 4 plus 6 minus 1, which is equal to 9. Irrespective of the number of segments, once the pipeline is full, it takes only one clock pulse to obtain an output. Pipeline organization is applicable in an arithmetic pipeline, an instruction pipeline which operates on a stream of instructions by overlapping the fetch, decode, and execute phases of the instruction cycle. Arithmetic pipeline. Arithmetic pipeline is used to implement floating point operations, multiplication of fixed point numbers, and similar computations in scientific problems. For example, a pipeline unit for floating point addition and subtraction. The inputs to the floating point adder pipeline are two normalized floating point binary numbers, x equals a into 2a, x equals b into 2b. Capital A and capital B are two fractions that represent the manticores, and small a and small b are the exponents. The floating point addition and subtraction can be performed in 4 segments. The registers labeled R are placed between the segments to store immediate results. The sub-operations that are performed in the 4 segments are: compare the exponents, align the manticores, add or subtract the manticores, and normalize the result. Compare the exponents, align the manticores, add or subtract the manticores, and normalize the result. The exponents are compared by subtracting them to determine their difference. The difference determines the number of shifts. Perform addition or subtraction with the manticore. When an overflow occurs, the manticore is shifted right and increments the exponent, whereas underflow occurs, the manticore is shifted left and decrements the exponent. The larger exponent is chosen as the exponent of the result. Manticores are added or subtracted at segment 3. The result is normalized at segment 4. For example, consider two floating point numbers in decimal form for simplicity. The two exponents are compared. 3 minus 2 equals 1. The larger exponent, 3, is chosen as the exponent for the result. The next segment shifts the manticore of y to the right to obtain the addition of manticores in segment 3 produces the sum. The sum is normalized to make non-zero first digit. Instruction pipeline or CISC instruction pipeline. Instruction pipeline reads consecutive instructions from memory while previous instructions are being executed in other segments. It causes the instruction fetch and executes phases to overlap and perform simultaneous operations. Computers with complex instruction require other phases in addition to fetch execute cycle. Computer processes each instruction with the sequence of steps: fetch instruction from memory, decode the instruction, calculate the effective address, fetch the operands from memory, execute the instruction, and store the result in the proper place. For example, 4-segment instruction pipeline. Fi is the segment that fetches an instruction. Da is the segment that decodes the instruction and calculates the effective address. Fo is the segment that fetches the operand. Ex is the segment that executes the instruction. The decoding of the instruction can be combined with the calculation of the effective address into one segment. Since the result is stored in processor register, execution and storing the result can be combined into one segment. This reduces the instruction pipeline into 4 segments. The instruction cycle in the CPU can be processed with a 4-segment pipeline. While an instruction is being executed in segment 4, the next instruction in sequence is busy fetching an operand from memory in segment 3. If an instruction is a normal instruction, then it will be flowing from the entire segment sequentially. In the absence of branch instruction, each segment operates on different instruction. Thus, in step 4, instruction 1 is being executed. The operand for the second instruction is being fetched, instruction 3 is decoded, and instruction 4 is fetched from memory. When instruction 3 is decoded and it finds that this instruction is a branch instruction, as soon as this instruction is decoded in step 4, the transfer from F1 to DA of other instruction is halted until the branch instruction is executed in step 6. If the branch is taken, a new instruction is fetched in step 7. If the branch is not taken, the instruction fetched previously in step 4 can be used. Pipeline conflicts. 3 major difficulties that cause the instruction pipeline to deviate from its normal execution are: resource conflicts. Attempt memory access by 2 segments at the same time. Memory of these conflicts can be resolved by using separate instruction and data memories. Data dependency. One instruction depends on result from previous instruction and it isn't available yet. Branch difficulties. Any instruction that changes the value of PC, such as branch. Conclusion. In this chapter, we have covered the following aspects of Central Processing Unit: General Register Organization, Memory Stack, 1 address and 2 address instructions, Data Transfer, Arithmetic Logical and Shift Instructions, Software and Hardware Interrupts, Arithmetic and Instruction Pipelines.